So here's our instrumental variable approach. So this is our last week class. So okay, here's a graphical illustration of the this is simple linear regression model. So this is outcome, right? And it has two components. So we have two sources. One is the part explained by X, right? The other is the part explained by U, which is red color. So here, red color is unobserved. So this is observed, okay? So these two are observed, but U is unobserved. So there could be, right? There could be something that influence Y, but I don't have a good, I don't know which one, right? What they are. But at least I can kind of conceptualize that there should be some factor that I'm interested in, and there's another factor that I don't know, right? So that is the basically the idea. And then I'm interested in computing the effect. So X times beta plus U is Y. And then we can see that there's no line between U and X, which means independence. Okay. So, well, to avoid unnecessary details, let's assume that the random variables are all normalized, centered, okay, mean zero. And then using that U is uncorrelated with X, we can actually compute it, express parameter as a function of the variance and covariance of the two random variables. So how to show that? Well, you can see that this is X beta plus U, right? And so then the numerator will be covariance of the X beta plus U, right? And then which is covariance X beta plus covariance X and U, right? And the second term is 0. Right? And then first term beta, okay, let's just assume that X is scalar, that it can go outside. And then that variance X will cancels, right? So we'll get this equality. So when when showing this one, what we really used is this one, right? Covariance X and U is 0. So this is critical. And how to achieve this? So basically, so we don't know, right? This is either we believe it, right? Either we believe it or we make it happen. And how to make it happen? One way, I don't have any control on you, right? I can't, because I don't know. I don't have any control on you, but I can control X. If I can control X, for example, if I toss a coin and assign, so X is 1 and 0, for example, and then if X equals 1, if it's head, and X equals 0, for if X is, coin is tail, that means this one is completely randomized. Okay, so if I completely randomize, that means that no matter what U is, they are independent, right? Because the event of the coin tossing will be random. So so I can create the random uncorrelatedness by randomization. Okay, so that is the idea behind this this assertion, right? In the completely randomized experiment, this assumption is achieved. Okay. Now, this is more realistic situation, right? Suppose we have this, in many cases, I mean, in the randomized experiment, then I can break down, right? Break this arrow. But in observational study, I don't have any way, right? I cannot really, break this arrow. And I'm interested in the effect of tau, right? Effect of t on y, which is written by summarized by tau. So this tau, the interpretation of tau is that if t were randomized, right? If t were randomized, then the effect on y will be characterized by tau, right? But they are not, right? So if they were randomized t were so if you're to randomize t, then tau is clear, well defined. But in this case, where we have arrow from u to t, we it's hard to achieve it. So one way is to introduce instrumental variable. Suppose we have a situation where there's another variable z. Z is totally independent of u, but have a connection on, it can affect t. And then in that case, we can do something. So z is a random instrumental variable. So the assumption is that we need three assumptions. First one is that relevance C has a causal effect on T. So C should explain T. Okay, should be related to T. And then, so basically it's all about the relationship between the three variables. Okay, so the relationship from of C to T has a direct effect. The relationship from Z to Y is has a dependence only through T. Okay. So there's no direct. Okay. There's no direct line. Okay. There's no direct line, but they are right. And Z and Y are correlated because of the relationship between Z and T and T and Y. So that is called exclusion restriction. So Z has a causal, okay, has a causal effect on Y. Oh no, sorry. Z causal effect on Y is fully mediated by T. That means Y depends on Z only through T. And then third relation, so 1, 2, 3, right? The third relationship is that the relationship between T and U is totally independent, uncorrelated. So that is the instrumental uncompoundedness. So Z is uncorrelated with U. So these are the three assumptions, and under these three assumptions, we can do something. Here's the main result. So so let tau Y is a tau T plus U. Okay. So that is the marginal relationship. But here, U can be correlated. So T and U is not independent. If they are independent, it's easy, right? If T and U are independent, it's easy. But T and U can be correlated. Then OLS cannot be used, right? The ordinary least square cannot be used. But if I have instrument variable that satisfies the above three assumptions in the previous page, then we can we can express tau as a ratio of the Z and Y to the ratio of Z and T. Okay. So here's a proof. Oops. Same thing. Tau T plus U. Tau T plus covariance right? So this is 0. This is tau is a scalar, so it can go outside. And then this guy is a denominator. So that means if you put this in the numerator, it cancels, right? So notice that is the hidden assumption is that covariance Z and T is non-zero. If they are zero, then you cannot really, it's not defined, right? And so that's actually by first assumption relevance here, relevance assumption. Z should be correlated with T. Okay. So that's fine. Now some so I'm gonna try to reflect what it really means, right? So I'm gonna have more thought on what it means. Okay. So okay. First of all, if Z is binary, then we have a very interesting sim result. Okay. So if Z is binary, then the covariance can be written as some function of the conditional expectations. And how to show that? Well, okay. So covariance Z and Y is a expectation of Z and Y minus expectation of Z, and Z is binary. So then let's assume that Z equal expectation is P. Okay. Z is binary, right? So then we can write. So then so we can write it. Oops. Same thing. And write it this way, of course. But Z can be either 1 or 0, right? So if Z is 1, right? So we use the fact that Z is just either 1 or 0, so then we get this result. So that means this is nothing random. So there's no, once you write this way, there's nothing left. So it's just no, actually that's not true. Okay, I think this is event, right? Event over Z equal 1. This is event. So, okay. We cannot write, okay. I think the first equality is not true. So, so this is y given z. This is about z. So that means we need to write it as a p z equal 1 times, no, not this way. I think this is, so it's not just, okay. Maybe this is better. Okay. Z equal 1 times 1 and, so this is a random variable, function of z. Okay. So what I wrote is like this. Plus sorry, this is should be correct. Because the the outer expectation is an evaluation of a function of z. Okay. And then take the expectation. So then, but we know that z takes either 1 or 0. So then that means penalty is equal 1 times the value of the function of z. Okay. Plus, oops, 0. Okay. Plus penalty z equals 0 times the function, right? The value of the function evaluated at z equals 0, which happen to be 0 if z equals 0. So that means we can write it as a p times expectation of y given z minus p square expectation y given z equals z plus p 1 minus p expectation, oops. Okay, we get this. That's the final. And then this guy is equal to variance of z. So that proves the first equation, right? Okay. Same way, we can do the same thing, right? So we just replace the rho of y to t and apply the same formula. Then we get the same result. That means the ratio, right? The ratio of the two, which is tau. The tau is the ratio of the two. So the ratio tau is the ratio of these two, which is ratio of these two. And then variance z cancels. And so it's just ratio of the two, difference of the two condition expectations. That is one comment. Okay. And then next comment, the second comment is that, okay, now this is originally, this is the definition of tau, right? This is the result of tau. And now let's divide it by variance of z, both sides. Okay. And then we can write the, right? Once you write it, this is the regression coefficient for the regression of y on z, right? And this is the regression coefficient for the regression of t on z. So then you can write this way. Beta regression of y on z, and this is the regression coefficient for the regression of t on z, right? So you can write this way. And then this one itself is not really it's not clear what it means, but once you see that, you can actually so if you define t hat, so if you define t hat to be the predictor of t using z, right? So t hat is a predictor. So using, you use the regression of y and z, right? And then apply them to z. Then this is a prediction of t. And then basically, this guy is a variance t, a beta t z square variance z, right? This is a beta t given z covariance z and t, z and y. So then the ratio, right? The ratio has some cancellation. So the denominator is this one, and then numerator with this part divided by this part is equal to this one. So this guy is indeed can be written as this, which means that this is so the tau can be regarded as a regression coefficient for the regression of y on t hat. That give us some idea of how to estimate tau. Okay, how to estimate tau. First, you use the regression of t and z to obtain t hat. And second step, you use the regression of y on t hat to obtain tau. So that is basically the idea. So two-stage, so this is a very popular technique in econometrics on how to deal with how to estimate the regression parameter when we have instrument variable, something like that. So regression, first regression of y on z to estimate the potential expectation, which we obtain t hat, and then regression of y on t hat to estimate potential expectation, and then is equal to tau. That is basically here, right? The formula equation 3 means that tau can be obtained by regression of y on t hat. That is this one. Regression of y on t hat. That is a two-stage least square estimator. So here's a graphical explanation of what's going on in two-stage least square method. So basically, we use the regression of, right, previously. So here, the difference is that the original graph in the original graph, there's a arrow here. So that is the problem, right? So this arrow basically prevent us to estimate the regression coefficient consistently. If you just use regression y on t, the OLS is biased because of this error, right? The independence does not hold. So that is the tricky part. So we want to break down. We want to break this error. How? By using the part that is not influenced by you. Okay, how to do that? Well, we use, because I know that Z is uncorrelated with U. You can actually do the regression of Y, I mean T on Z, right? So to get T hat. So once you obtain T hat, which is a function of Z. So once you do that, this T hat is a function of Z. So then this guy. So basically you have two parts. You have a T hat part and then T minus T hat part, right? And then this guy is independent of this one, and this guy can be correlated, right? So basically idea is, okay, I'm going to use only this part. And then that is this error. Okay. Then the amount of the factor, right? The amount of is this one, right? T hat is Z times this guy. And now the formula is equation 3. Equation 3 tells you that the amount of the regression coefficient for the regression of Y on T hat is exactly equal to tau. The same tau that we originally interested in, right? So that is a surprise. So that is very good news, because then I know that this guy is independent of the U. So I can apply, regression, standard regression. And another interesting part is that, okay, so what if you just the regression to the regression of Y on Y, I mean C on Y? What is the regression, right? What would be the regression coefficient if you directly regress to the regression of Y on Z? That is this guy. Okay, right? So that means what? You should get the same answer, right? Whether you regression of Y, I mean Y on Z, right? So from Z to Y, that's one pass. Another one is from Z to T hat, and then T hat to Y. Okay, so then that should be the same, right? So that means that your Z, okay, Z times beta T hat Z times tau should be equal to Z times beta Y and Z. Okay, so that's basically means what? Tau is beta Y given Z divided by beta T and Z, which is exactly what we showed, right? What we started with here, this one. Okay. So that's a really nice way of explaining two-state research here. So I thought that's very interesting. So as long as you can find Z, which is totally irrelevant to with unconfounding factor, then you can basically achieve causal inference, even if there's a So compounding factor can affect treatment. So that's a very powerful tool, and it's very popular in econometrics and social science, because in social science and econometrics they cannot really do the experiment to human, right? I mean, so that they always use observational data, but they are interested in causal inference. So then this instrumental variable approach is very powerful tool. Okay. So this is non-compliance problem is one special example of the instrumental variable approach. So we use this one as an example, application example of what's going what's the how the instrumental variable idea can be used to solve our problem. Okay. So what is the non-compliance problem? Is that okay? The in many cases doctor or so we could if you do experiment, right? So for example, kineology, professor recruit people and then want to investigate the effect of the daily exercise to health, for example, right? And then they have a randomized group and ask one group to do exercise, every day for 30 minutes minimum, and the other one don't exercise, something like that, right? Well, that's a kind of that's Z, okay. But people, right? So even if you are asked to do exercise, you may not comply, right? You may not comply. You are lazy or you are too busy, something. You may not, react according to what you're asked to do. So then the actual treatment could be different from what you're assigned, right? Even though there's maybe there's some high correlation, right? Many people will comply, but some people may, do not comply. So that is the kind of interesting, realistic situation. So Z is the treatment assigned, and T is the actual treatment received. So then we may not have we observe Z and T, of course, but we can sometimes we don't have a sometimes we don't have a equality. Then that problem is called a non-compliance problem. Okay. And so then T is actually the reaction of people, right? So then you could view it as a potential. It's not potential outcome. It's more like a potential treatment. Okay. And then you may heard about this. So that means you can actually think of 4 groups. So we have a 4 possibility. Some people may just do no matter what, right? So that means always taker. So T equal, even if they are not, so even if so C equal, right? This is C. So C equals 0. Even if they receive Z equals 0, they just do it. They is always taker. Complier, they follow, right? If they are asked to Z equal 1, then they take it. If they are asked to take the control, they follow. So that is the compliers. Defiers are so defiers are very strange, right? If they are asked to follow, they don't. And if they does not follow, asked to does not take the control, then you take a treatment. So that's a tricky part, and never taker is relatively easy. So always taker and never takers are relatively easy. They just do the same thing, right? No matter what they are asking. But the defier is a little bit tricky. Okay. So maybe we need some assumptions, some simplified assumptions. First assumption is this. It's called the monotonicity. So basically it means you cannot have what is the characteristic of this? So if g equal 1, t equal 0, g equal 0, t equal 1, this is defier. Right? So the probability of defier is 0. That means there's no defier. So we are not going to. So there maybe exists like maybe a 0.1% of people can do that, but that's probably not really significant. So we just ignore this extreme. There's always some extreme people, right? There's always some strange people, but we are not really do that. We are not going to do so we'll just ignore for our analysis. So that's the monotonicity. And exclusion restriction is that, okay, for always takers and never takers, we never observe, we have no chance of observing counterfactual outcomes, right? We only, so that means for the always takers, we never observe y0. For the never takers, we never observe, we have no chance of observing y1. So there's nothing we can do. So that means, okay, let's just assume, make life easy. And let's just assume that for these cases, we are not really worry about. We'll just make a simplifying assumption. So, so when when you do some decision, we assume that the decision will make some change, right? So that means for these people, they will not follow anyway. So maybe we don't have to worry about these people either. Okay. So monotonicity means that there are no defiers. That's right. So if monotonicity holds, that means the property of, right? So this will be an implication, but you can observe it. You can test it from the sample. We can actually you observe this group, and so you can actually check whether this monotonicity is true or not. So this is one part. And exclusion restriction means that the potential outcome is a function of t and does not depend on z. The y, potential outcome y of y. So the value, the outcome, the health outcome, for example, it depends on what you actually treated, right? Rather than what you are assigned. Which kind of makes sense, right? Okay. So this is I think this Invens got a Nobel Prize. Anyway, so they have this very famous result. So basically, they are interested in the average treatment effect, right? So estimating the average treatment effect, but not for the whole population, rather it is for the among the compliers group. So this is complier. So among the complier, what is the average treatment effect. And it is often called average local average. So because it's a subset, so we use a local average treatment rate or complier average causal effect. And under the monotonicity assumption and exclusion restriction assumption, we have so what? How to show that? Well, okay. So basically, this is the difference. The overall average treatment effect on Y, and this is the average treatment effect on T, right? And so this is the ratio. So what is the tau Y? Tau Y is this. Right? That's the definition. And then we can kind of write it as a always taker times probability of always taker plus we have four groups, right? So we are going to do this decomposition and complier defier plus oops or never taker because we kind of stratify, right? So this is the overall mean, and the overall mean is just we can stratify, and for each principal stratum we have a conditional expectation plus times the proportion the group. Okay. And first thing is that okay, so defier is 0. The probability of defier is 0, so we don't have to worry about the third line. For always taker, right? If it's always taker, for always taker, these two are equal. That's the exclusion. That is the exclusion restriction, right? So the exclusion restriction says that always taker and never takers have the same potential outcome. So always taker, never taker, they are all equal. So third line is 0, and first and fourth line is also 0. So we only have a second line. And this is, so that means this is what so that means we have a tau C, right? Times probability of a compiler. And same way, we can do the same thing to T, right? So how T is defined to be this. So that means we can actually right. So this is okay, right. So then then we can do the same thing, right? You can, do the same decomposition. And then what is but the definition of using so now let's use the definition. So always taker, right? Always taker means that these two values are all equal to one. One minus one, right? So that's the zero. Complier, one, right? Tau one will be one. Tau zero will be zero for compliers. So that means this is actually property of complier. And the others are all zero. Defier, will be tau one will be zero, tau zero will be one, but we have a property is zero. Third one, this is never taker, zero minus zero, which is zero, right? So then we have this. So now we have so tau c is a tau y divided by this complier, tau complier, but this property of complier is equal to tau t. So that basically proves this equation 5. Okay, now we have this one, and furthermore, in addition to the above two assumptions, if C are independent, then we get so tau c. Okay, so tau c is what? Tau c was previously is a expectation of tau y minus tau t, which is expectation of y1 minus y0 complier. Oops, no complier. Sorry. Okay. I think so how to show that? Okay. Z independent. Okay, so let's just seems to be yeah. I will come back. I don't know. I forgot about how to prove it. I should have. I think anyone has an idea. should be related to instrument variable because Z or do we just do it something like this? I think something like that. So if you do that, you can we do the same technique. So we have a how to do that property y is equal 1 1 minus c equal 1, right? Plus property c equal 0. And then p, so for example, p y. So what is y? Y is y t y1. Yeah, I should have. Okay. Huh? But C, so we usually use the independence. C is independent. So there may be a, so I think, okay, maybe I should start from 6 and show equality. So if I use this definition, right? So, and then what is the numerator? Oh, so then expectation of y is equal 1 is expected value of t y1 plus 1 minus t y0 given c equal 1. Something like that. So so t and y could be put in, right? We uh, so that's right. So if because we take the minus, so this part, okay, right? So I guess expectation of y0. Yeah, I think we and then what I'm saying uh, t t times expectation of y1 minus y0 given c equal 1. So then this guy will be removed and then right? Well, I will maybe I will prove it the next this Thursday. Let's but once you so that was kind of obvious, but I couldn't recall exactly. There's some steps I should uh write down. But let me go back to this example and then come back and see whether I can prove it. So here's a illustration. So this is the actual observation, right? We observe T, Z, and T. So that means we can actually you can view it as a mixture distribution because what does that mean? If someone has a Z equal 1 and T equal 1, what does that mean? That means he could be either complier or always taker, right? So that is depends on what potential outcome is. So so this one only means shows that this one is okay. Your T1 equal to 1. That's all you so that's the only evidence, right? That's the only one. So this is only one. And then this one, I don't know, right? So that means I have two possibility. So one is this one is 0. Another one is this one is 1. If this is 0, that means this group is called complier. If this 1 and this is also 1, then that is called always taker. Okay. The same thing here. So this one basically says that your T1 is 0. So that means it can be either never taker or defier. Right? So that's so then this one is so this is actually the what you know for sure from the observation, and this is a possibility. Okay. And now interesting part is that we assume that there's no defier. That means we can exclude this possibility. Okay. We can exclude this possibility. That means you can see, for example, in this situation. So this the consistent group, right? T and Z are consistent group. They are inconsistent group, right? So if they are inconsistent, that means we have only one possibility. So because of that, right? Because of that, I can see that okay, among so basically in this population have a like a 80K. So in this population, I have about 20K always takers. Okay. And then and then this group, I mean, so this is basically 80 and 50. And then how can I split? So the real question is so this is what I observe, right? This is my observation. How can I split these numbers into two groups? How do I know that? The idea is okay. The idea is okay. I randomize Z. Okay. So that means okay. I randomize and then the proportion of so this guy essentially goes to here. And this guy essentially goes to here. the basic why? Because I want to know the proportion of the never takers among very confusing among I want to proportion of never takers, and then what I know is that in this group, I, right, I have this proportion as a never takers, and basically Z is completely random. So that means uh, among t equals 0, right? T equals 0. So basically this is okay. So 20 always taker. But this part is randomized, and that gives you some hint how to decompose. Uh, Very straightforward, but I couldn't. So I maybe I need to well, you can think about that. I can explain this Thursday class, but the idea is basically this one gives the idea of the how to split. So the neighbor taker, so this neighbor taker information can be used here, and then compiler. So always taker can be used here to get the proportion of compiler. And then once you do that, then you can basically tau. Yeah, this is what you have end of the day. And so you can actually, so we are interested in estimating tau. So among the compiler group, we want to compute the treatment effect. So that means compiler group, the treatment Y. So so compiler, right? So we have a compiler. This is a t equals 0, t equals 1. And so among the compiler, t equals 1, Y is 40. Compiler t equals 0 is 10. So we got this one. Or we can use this formula 6, this formula, then you can do the same thing. So you can basically use only C variable right? The observable data only without really walking through this partition. You apply this formula and then obtain the same answer. So that is the idea. So that but I forgot how to derive. So this how to derive that actually is a way to understand, has to do with causal inference, because so this one, right? So what's the connection between the this one and the instrumental variable? So G is the instrumental variable, treatment assigned, and T is the treatment at so treatment assigned, and this is a treatment taken, and this is our okay, right? This is our formula. This is our formula, but the tau, because of the exclusion restriction, the meaning of tau changed because to tau c, because we assume that the always taker and never takers doesn't change. So the meaning of tau is changed to tau c. Then this instrument variable formula can be directly applied here. This is what we already proved it, and then we can obtain the same result. But I'm sorry, I didn't I couldn't remember the details of how to derive this, but I will back up in this Thursday class, or write a supplemental document. The current plan is that Dr. Chen Lin Lee will give us guest lecture, because he's an expert in instrumental variable approach, and so he might have something to present this Thursday class. So let's welcome him. But if not, I will cover some other topics too. So okay, that's all for today.